my colleagues from Italy. Okay, so here is the motivation. Usually, concrete runtime values of objects in some debugged programs are ephemeral. So, what if we persisted them, to some persistent database on disk? So currently there are two existing approaches which are focused on this. The first one is example-based approach, but this lacks scalability. So it's not for large object graphs. It's usually just from some small objects of, I don't know, a few sub-objects, not for, I don't know, megabytes of large memory object graph. And the second approach is omniscient debugger or record and replayer technique, which uses opaque storage formats, and they lack some easy queryability. You cannot easily query the saved values. So therefore we designed RuntimeSave, which is an approach that stores runtime values of variables collected from the Java virtual machine and some associated metadata into a Neo4j graph database. So it is basically a middle ground between these two existing approaches. It combines easy queryability using Cypher language, which is included in Neo4j, and on the other hand, it has sufficient scalability. So the number of saved nodes with respect to number of saved nodes, edges, and speed. So the first part of our approach is data collection. So imagine some program running in an IDE, and it is currently in a debugger. So the developer can choose three options how to save some objects from memory to disk. The first is manual object selection, when the developer just clicks, for example, some variable in a variables view and chooses the option like save this variable because I don't know, I like it because it's related to some bug I'm working on. So it's interesting and I want to save it on disk and maybe add some note to it. The second option is save points. Save points are an alternative to breakpoints. But instead of pausing the program, as breakpoints usually do, we just save all the variables currently in scope to a database and then continue running the program. So this is the goal. The third option is sampling. Here we collect the values of variables from every nth executable source code line for the first t executions. So basically, if we set the n and t to infinity, then we have basically a full tracer or full recorder of the program. Now continue with the graph model of RuntimeSave. We have a two-layer model inspired by Git internals. I don't know if you know how Git works by its internal working, but basically in RuntimeSave we have hash nodes. So this is a layer of nodes with hashes assigned. This includes stack frames, objects, arrays, strings, primitives, and null. These are the nodes which are mirrored from the Java memory. So we just mirror the Java memory graph into our hash nodes. And the second layer is some layer above this one, which stores metadata related to these hash nodes. So for example, we can create some location information like class, method, line number, free text nodes, and many other possibilities. And these metadata nodes point to these hash nodes and tell us something more about, for example, this node is important because it is related to some bug, this node was collected from line number 40, and so on. So here is a specific instance of our graph model. So we can see, I don't know, this frame node, string node, object, primitive array node, which are basically just straightforward mirrors of the Java memory graph. So it's quite simple. And then we have this metadata layer up here, such as node, line, method, class, and we can see they point via edges to the hashed nodes. Each hash node again points to some other hash nodes using some relations, which are labeled by type has field, with the property name of family and so on. So this basically is a representation of some object which has fields, I don't know, some stack frame which has variables, array which has elements and so on. So this is basically stored in the database in Neo4j. It is quite straightforward. If you can think about it, it's just one-to-one mapping between JVM, there is an object graph, and this is basically the same, almost the same as the graph in Neo4j. So it's quite simple. Now, where's the catch? Why is not so simple? The problem, of course, is performance. This is totally slow. It's absolutely unusably slow. We just map this naively without thinking more about it. So we created some approaches to speed up the saving process. The first approach to speed up saving is packing. Packers are graph shape simplification transformations, which we optionally apply before storing values into database. So they first reduce data volume, which is faster, and then they also, by the way, simplify comprehension by humans. This is some byproduct. For example, a sparse array packer replaces all array nodes. So, for example, this can be a node containing edges pointing to, I don't know, 1,000 nodes. So it's large array. It replaces them with just one simple node of type sparse array, which contains some metadata or some information that it has a length of 1,000 and it contains only zeros. Yes? So it is like replacing 1,000 nodes with one node, which speeds up saving. In other packers which we created are linked list packer, same primitives packer, primitive array packer, and so on. So this is an extensible approach with some domain-specific algorithms which simplify the graph to contain less nodes, less edges, and be faster and more and easier to comprehend. Now the second approach to speed up is hashing. This is focused on deduplication. Well, you can imagine that a large object graph in Java has so many duplicates. Yes, basically there are maybe, I don't know, many similar arrays of similar objects which are differing only by very small parts. So deduplication is causing faster storage, also less storage space. How do we hash these nodes? We use a content addressable system inspired by Git internals. So again, we're inspired by Git, which uses this content addressable system. It is based on Merkle trees, but again, here's the catch. We have a graph, not a tree, yes, so this is the problem. Now, what are our conditions which must be fulfilled? So first one, nodes with the same hashes are equal by deep value-based equality. So this is the main condition, main goal which we should fulfill with our hashing. So basically you can say that, okay, these two nodes have the same hash, so then absolutely they are value equal, yes, recursively value equal. All these big graphs are equal if these two nodes have the same hashes. This is also how Git works. So we devised a custom graph hashing algorithm which has these properties, these requirements. First, hash is computed for every node, not only for the whole graph, but for every single node which has a unique hash. And we can identify each given node with this hash. Second one, we should avoid encoding which node is a root, of course, because we can point to any node in this large graph and consider it a root. So there is no one single root of the whole graph. We can select some subgraph and say, okay, so now we have this subgraph and this is now our root. The third property is that each node's hash encodes the node's labels and properties, such as, I don't know, the name of the variable and so on. Then the properties of the outgoing edges. And third, recursively the same for all reachable nodes and edges. So this hash encodes not only the node itself, but the whole subgraph which is reachable from this node. And the fourth property is that there are no hash collisions in practice. This is like in Git. if we had hash collision, there would be some data loss, yes. This is how Git works, and this is also how our approach works. It works in practice, yes. It is not in theory, but in practice, yes. So here is some specific example. We can have this one graph on the left stored in our database. These letters A to F are some specific hashes. Then we have this second graph which we want to store in our database now. You can see that many of the nodes have same hashes. Yes, this is like almost the same graph. I think that just B and C are swapped. Yes, they are absolutely the same, but B and C are swapped. So this is just the only changed. And you can see that we quite well deduplicated the graph because there are not like, I don't know, 6, 12 or so nodes. There are just, I don't know, 1, 2, 3, 4, 5, 6, 7 nodes. Yes, so there is great deduplication. We reused the existing parts of the graph, and it is saved quite well. We can see an important property here that all the relationships of reachability are preserved with our hashing. So, for example, if this A has an edge called 1 that points to C, which points via an edge called A to E, which points via an edge A to F, and so on, this reachability transition is preserved in the final graph. So we can just trace it here. A points via 1 to C, C points via A to E, E points via A to F. So this whole reachability transition is preserved absolutely in the original, from the original graph in the result. So the querying is absolutely natural. It's really like what is reachable in the origin that is reachable in the database. Okay, now again here's the problem. Some nodes have the same hash, but they are not reference equal, because we can have some specific cases when two nodes have the same hash, but they are really just copies of the same data. So we solved this by computing the ID hash of each node. The ID hash of each node encodes its hash, its copy number, which is just the DNS traversal order, and the hashes and copy numbers of all reachable nodes transitively again. So here we can see just a small example again. This is our original graph. These indices are copy numbers, yes. So this is hash B copy number 1, hash B copy number 2, and copy 3. This is what we want to save into database, and this is the resulting deduplicated graph. Now, of course, the result is not totally deduplicated. This is not absolutely perfect. There are some instances which are not perfect deduplication, but it is nevertheless something reasonably well performing. Okay, now we have everything we want to save, so we can save the graphs finally into database. Now we use each ID hash of each node as a unique constraint. So we cannot have two nodes with the same ID hash in the database. This is a unique constraint. Now our graph is condensed into a directed acyclic graph, and redundant edges are removed. So we have basically some dependency graph of nodes, and we traverse this dependency graph from the root. So we first try to insert the root node, and if this root node is already present in the database, we just stop. So we have, for example, a very large graph of objects, for example, a megabyte large of objects, and we see that the root of this graph is already present in the database using this ID hashing comparison. We just stop and everything is solved. Otherwise, we continue recursively inserting the target nodes, traversing this directed acyclic graph. Again, we continue until we again find some ID hash which is already present, and then we stop. Okay, so we perform some preliminary evaluation of our approach. We tried saving all variables in scope for the first execution of each line, but that slowed down the program like 30 or 40 times. Yes, so it's really, even after the optimizations, it's really slow. So just some anecdotal evidence, it slowed down the program before these optimizations like 3,000 times. Yes, so it was unusably slow. Now it's just slow. But the main problem is really technical, because just using Java debug interface slows down the program 10 times without doing anything relevant. So this is just a technical thing. We should improve it in the future. Now we perform some other evaluation, which we focused on the number of nodes, edges, and the insertion time, but without using JDI. We just mocked it with some other approach. So now we compared a plain approach without any optimizations. We just straightforwardly mapped the Java memory graph into Neo4j database without doing anything important. Then we just used our packing, then only hashing algorithm, and then we combined both packing and hashing. And you can see that the number of nodes dramatically reduced. This is like 50 times reduced number of nodes. 20 times number reduced, the number of edges, and more than 10 times improvement in the insertion time into database. So this is really drastic improvement when you compare the plain approach with our packing and hashing. So this really helps with scalability. What are the applications of RuntimeSave? We can do some querying on it. Yes, of course, we have this language called Cypher, which is great for querying graphs. We have visualization for free. We can just open many existing visualization programs and just explore our graph. We can start even a program at any line. This is our demo, which we included in the paper. Well, what is the problem with starting a program at any line in general? The problem is that we don't have local variables in scope available. Yes, every line in the program needs really some variables, some specific variables to be started, but we can easily load them from the database. We already saved them before, so now the problem is basically solved. Just load the correct variables and it's solved. There are other applications like program comprehension, API exploration, storage of some values for unit testing. Use it as a team's knowledge base, software repository mining using runtime data. Yes, so you just don't do repository mining using source code, but using runtime data, using variables. Yes, so there are so many applications. You can imagine almost everything. So in conclusion, RuntimeSave is a reasonably performant approach for saving values of Java variables using from Java variables from runtime using this Neo4j graph database. It is available as an IntelliJ plugin at this address if you want to try. And as a future work, we should replace Java debug interface with bytecode instrumentation. This is a speed up improvement, and maybe better support some data editing, deletion, because now we can insert values into database, but yes, editing is quite not yet good for now. There are many other future ideas. You can find them in the papers. In the paper. Okay, so that's it, and thank you very much.
Well, thank you very much for the great talk. And do you have any question?
Well, using the garbage collector, yes.
Well, the garbage collector is traversing the heap for you, right? So you find all the objects.
Yes, it finds all the objects, but the garbage collector runs at some unpredictable times. And well, my aim is not to save just any values, some random values. I would like to save some specific values. For example, the programmer would like to save, I don't know, the first value that occurred at this line, for example, yes. Or I don't know, he would like to say save a value which is equal to 10, and if this value is equal to 10, then it saves, I don't know, these referred objects. Yeah? So the programmer should specify using these save points, or using some manual selection, or using some sampling criteria, which values should be saved. So my goal is not to save any values at all, like save these values, I don't care. I should save just some specific values, yes, but if I wanted to save just any values at all, like absolutely irrelevant which one, at which time point in the execution, if it is at the beginning of the program, at the end of the program, in the middle, if that doesn't matter, then yes, it would be possible to use garbage collection. Thank you.
Maybe I can get that clear. Every time you have a write that object updates some part of an object, the hash of the object and everything that points to that object needs to change?
Yes, so every object, the hash of every object includes or encodes the hashes of all referred objects. So, for example, this.
The closure of the object, which would be half the heap.
Yes, it is really. It is really important point. This could be half a heap. If this is the case, then we just traverse half a heap and store half a heap. Yes, because there is no practical solution to this in general. But our main problem is maybe it is not the collection itself. Really, the currently which I encountered was that the bottleneck, the time bottleneck, was currently saving to database. Yes, because saving to database is I/O. It's input/output. It's really slow. It's using TCP packets and some disk access and so on. So currently, I focused on this saving part. So yes, at each point I would like to say some variable. I traverse the whole part of the heap which is relevant. And then, yes, using some optimizations, I try to condense it or try to somehow simplify it to simplify the saving part. Yes, so the saving part is optimized. I don't save too much data, but yes, the traversal part of the graph is not yet simplified, and I should just traverse everything that is necessary. Thank you.
So a follow-up would be, if you have data structures that are immutable, which means no updates, could you do something better with the hash?
Yes, if we had only immutable data structures, then it would be really simple because we can just see that this object didn't change during this time, so we could just assume that its hash is the same, and we shouldn't recompute its hash. So yeah, that would simplify a lot of things. Thank you.
Okay, thank you for the question.